Polyamide is a polymer of amide monomers. Polyimides have been in mass production since 1955. With their high heat resistance, polyimides enjoy diverse applications and applications demanding rugged organic materials, for example high-temperature fuel cells, displays, and various military roles. A classic polyimide is Kapton, which is produced by condensation of pyromellitic dianhydride and 4,4-oxydianiline. Classification: according to the composition of their main chain, polyimides can be aliphatic, semi-aromatic, aromatic. These are the most used polyimides because of their thermostability. According to the type of interactions between the main chains, polyimides can be thermoplastic, very often called pseudo-thermoplastic. Thermosetting: commercially available as uncured resins, polyamide solutions, stock shapes, thin sheets, laminates and machined parts. Synthesis: several methods are possible to prepare polyimides, among them, the reaction between a dianhydride and a diamine. The reaction between a dianhydride and a disocyanate. Dianhydrides used as precursors to these materials include pyromellitic dianhydride, benzoquinone tetracarboxylic dianhydride, naphthalene tetracarboxylic dianhydride. Common diamine building blocks include 4,4-diaminidiphenyl ether, metaphenylenediamine, and 3,3-diaminidiphenylmethane. Hundreds of diamines and dianhydrides have been examined to tune the physical and especially the processing properties of these materials. These materials they tend to be insoluble and have high softening temperatures, arising from charge transfer interactions between the planar subunits. Properties: thermosetting polyimides are known for thermal stability, good chemical resistance, excellent mechanical properties, and characteristic orange-yellow color. Polyimides compounded with graphite or glass fiber reinforcements have flexural strengths of up to 50,000 assigned flexural moduli of 3 million SI. Thermoset polyimides exhibit very low creep and high tensile strength. These properties are maintained during continuous use to temperatures of up to 452 AA°C and for short excursions, as high as 704 AA°C. Molded polyamide parts and laminates have very good heat resistance. Normal operating temperatures for such parts and laminates range from cryogenic to those exceeding 500 Fahrenheit. Polyimides are also inherently resistant to flame combustion and do not usually need to be mixed with flame retardants. Most carry a UL rating of VTMO. Polyamide laminates have a flexural strength half-life at 249 AA°C of 400 hours. Typical polyamide parts are not affected by commonly used solvents and oils including hydrocarbons, esters, ethers, alcohols and freons. They also resist weak acids but are not recommended for use in environments that contain alkalis or inorganic acids. Some polyamides, such as CP1 and CORINXLS, are solvent-soluble and exhibit high optical clarity. The solubility properties lend them towards spray and low-temperature cure applications. Applications: polyamide materials are lightweight, flexible, resistant to heat and chemicals. Therefore, they are used in the electronics industry for flexible cables, as an insulating film on magnet wire and for medical tubing. For example, in a laptop computer, the cable that connects the main logic board to the display is often a polyamide base with copper conductors. Examples of polyamide films include Apical, Kapton, Upalex, VTECPI, Norton TH and Captrex. The semiconductor industry uses polyamide as a high-temperature adhesive. It is also used as a mechanical stress buffer. Some polyamide can be used like a photoresist. Both positive and negative types of photoresist like polyamide exist in the market. An additional use of polyamide resin is as an insulating and passivation layer in the manufacture of digital semiconductor and MEMS chips. The polyamide layers have good mechanical elongation and tensile strength, which also helps the adhesion between the polyamide layers or between polyamide layer and deposited metal layer. The minimum interaction between the gold film and the polyamide film, coupled with high temperature stability of the polyamide film, results in a system that provides reliable insulation when subjected to various types of environmental stresses. Polyamide powder can be used to produce parts and shapes by sintering technologies. Because of their high mechanical stability even at elevated temperatures, they are used as bushings, bearings, sockets or constructive parts in demanding applications. To improve tribological properties, compounds with solid lubricants like graphite, PTFE or molybdenum sulfide are common. Polyamide parts and shapes include P84NT, VTECPI, Meldin, Vespel and Plovis. In coal-fired power plants, waste incinerators or cement plants, polyamide fibers are used to filter hot gases. In this application, a polyamide needle felt separates dust and particulate matter from the exhaust gas. Polyamide is also the most common material used for the reverse osmotic film in purification of water, or the concentration of dilute materials from water, such as maple syrup production. The Icaros solar sailing spacecraft uses polyamide resin sails to operate without rocket engines. See also, polyamide, polyamidamide, polymerization, references. Further reading, Modern Plastic Mid-October Encyclopedia Issue, Polyimide, Thermoset, page 146. External links, Material Property Database, MIT.